Did we never equation? Yeah, basically. I didn't small.
Really close.
I get a situation where it's like 1 year. Also, I did just explain myself like I realized the stream. Yeah. There's issues. Yeah.
You have to basically
I still have like some. Probably not at this stage. This is not. I probably think I might do that fucking thing, but I didn't switch. Well,
all right, let's go ahead and get started. On a side note, so I ended a few minutes early last time, and then a bunch of you came up and asked really interesting questions at the end, and I like that a lot. But do it during class. I mean, they're good questions, and I would actually, it's much more fun for me. I don't really like to monologue, right? I mean, maybe my actions don't suggest that that's true, but I'm much happier if we have those questions come up, because probably everybody else has those questions too. So I'm almost tempted to like end early just to make sure you ask questions, but I've got too much to say today. Okay, so I've been sort of hinting at it for a few lectures here, but I want to give you the basic core ideas from controlling a more complicated robot, right? So a humanoid is the canonical one, but this will be also relevant if it's a complicated quadruped or you know, in general, something that's got a lot of joints, and those joints are legs, appendages that are trying to move around. Okay, so you know, in our discussion of legs so far, I really continue to love the simple walkers because I think they really shed a light on the core problems in locomotion, right? And I really think it is important and helpful to think about these pictures like the hybrid dynamics and understanding that we can take our tools from trajectory optimization. We could take our LQR tools and make it work for these systems, our sums of squares tools, you know, our Lyapunov methods. We can adapt them to this more complicated context. And we've been doing that over the last few lectures. And also, I guess another side note is I'm actually working really hard on that group of notes. I'm sorry that maybe I put too much effort into them and they're not ready yet, but they'll be ready in time for your project, for instance, and they should be up soon. So, you know, those tools all work, and there's even more tools that I didn't cover in lecture about stabilizing trajectories. We did the fixed point, but stabilizing trajectories, computing time-varying Lyapunov functions along trajectories. How do you stabilize a trajectory when you have to make sure that you handle this discontinuity? There's nice ideas there. I'll leave those to the notes so we can move on to humanoids. Okay, so this path, though, is a path where there's a lot of work to do nonlinear optimization, even for a 2-link robot. You have to be careful about the guards. If I go to a kneed robot, then it gets a little bit more complicated. And if I want to add, 2 knees, an ankle, it's getting a little bit more complicated. My nonlinear programs are running a little bit more slowly. I'm a little bit less sure if it's going to find a solution. I'm going to add a hip, arms, and it's just, I feel like the weight of the universe is coming down on me because my optimization is not as is going to be as strong. But at the same time, I've showed you these videos of a full-on humanoids running around. So something doesn't compute. And there's something that happens, which is that as you add more and more complexity, it gets worse and worse and worse until it starts getting easy again, right? Somehow, when the robot has enough joints and enough control over those joints, somehow it gets easy again. And I want to tell you that story today to make sure you understand that there are simplifications if you can assume that you can basically do what you need to do with your foot relative to your mass, that take away a lot of that complexity again and allow sort of a 2-stage approach to the problem, and that's what's fueling a lot of the successes you see on the complicated robots. Okay, so I like to think about this actually with a sort of a silly, maybe, but a thought experiment. So imagine you have a spacecraft. I know some of you guys actually have a spacecraft. Mine's just a box, sorry. But imagine you have, I don't know, let's say it's fighting gravity, so it's not really, or it's close to a planet, or it's a hovercraft, or whatever you want to think. But I've got some system that has a mass and inertia. The mass is at location x, y, and it's got some orientation. Okay, and I want to fly this thing around in the gravity field. And let's say I've got some thrusters available that can produce some force. Maybe they're cool thrusters. I can do a little bit of thrust vectoring on them. So there's some force coming from here, some force coming from here. Maybe there's even another one over here. It's producing some force 3. Okay, and I'd like to just drive this thing through the gravity field by commanding forces at the thrusters, possibly vectoring. So this is a lot like the planar quadrotor that I wrote down before, but if I allow vectoring here, then actually I have even a simpler problem than the planar quadrotor, where the quadrotor was restricted to produce thrust along the axis of the rotors. This one, I'll say it can produce forces in either direction. So if my inputs are force 1, however many I have, and they live in R2 because I'm in the plane here, so I get to control x and y of the force, then my dynamics become, actually all the hard parts of the dynamics disappear, and I really just have the center of mass that moves according to the total x component of the force, right? I have the z motion of the center of mass. I said y here, let me call it z. That's just going to be the z component of the center of mass minus mg. And even the rotational parts, if I just say that these things are at positions r1 from the center of mass, there's some vector r2, r3, where the force is being applied, then the total moment coming from that is just Ri cross Fi. And the only thing affecting it in here is actually the moment coming out of the plane, so the y component of that resulting vector, right, which is Rix Fiz minus, or yeah, Friz Fix like that, right? So this system, even though the planar quadrotor was a nonlinear thing, we had to linearize it or whatever. If I'm willing to tilt my rotors or have my thrust vectored, then actually the dynamics are linear. Well, they're affine. I have a gravity term here, but the forces all appear linearly if the locations here, of course, are constant. This is actually an affine dynamical system. I can use all my standard tricks to control it. I can change coordinates and do LQR if I want to stabilize it. Right, I just have to have some thrust that cancels that out to get rid of the affine term. I can do trajectory optimization with with convex optimization. I can do all my tools, right? Okay, so let's make it a little bit more interesting. Let's say that that I have some limits on my forces. So before, my thrust vectoring before was that I could only apply force in a particular direction. Maybe I had a saturation. But let's say that these things are small thrusters. I can't produce arbitrary forces. So I could do like subject to some constraints that, let's say, the magnitude of F is somehow small, right? Well, if I'm willing to write constraints of this form, I can potentially still do convex optimization against it, especially if I say every element of F, let's say Fix is small, Fiz is small. Okay. And that makes the problem a little bit easier, but actually doesn't break the complexity class. I can still do convex optimization on it. All right, so just for fun, let's think about some spaceship where the crew can actually take. I mean, this does limit what the spaceship can do. So let's say that the crew can actually go and grab a thruster and actually move it to some other place on the spaceship while it's operating to overcome this fact that they've got tiny actuators. But if they want to accomplish some task, they're allowed to move the thrusters as they go. It's a little silly, but there's a rule. Okay, you have to turn off the thruster when you're moving it, because that's probably dangerous, right? So I guess yeah. So you turn off the thruster. It takes a little bit of time to move, and you put it down. You turn it on again. How do you control your spacecraft like that, right? So. But if I say, for instance, r dot has got to be small, so it takes some time, like a velocity limit. Already, if r becomes part of my actions, the system suddenly becomes bilinear. So I've gotten a more complicated problem like this. But even more so, if I were to say that there's a constraint that r dot times, so the magnitude of F has to equal 0, you can't have force while your actuator is moving. That's a lot. That's like my complementarity constraints before. That gets a lot harder, right? It's also still ridiculous, and you're wondering where I'm going with this, but I'm almost there. Okay, so now let's say there's even one more constraint. You're allowed to move your thrusters around, your thrusters around to accomplish the task, but you can actually only turn them on in certain locations. Okay? So let's say as my ship is flying through the air, maybe there's actually only a few locations, even in the world coordinates, where I can turn it on if my thruster happens to be inside here, okay? Or I could turn it on if my thruster happens to be inside here, but everywhere else I'm not allowed to turn it on, okay? So suddenly, kind of a weird game, probably something like, there's probably an Atari game that did that, or, you know, or some, yeah, Nintendo or something, right? Okay, you only allow it in a few locations, right? So you can imagine that. You're moving along and you just have a few opportunities to sort of push, and you could maybe schedule your spaceship to fly past the regions where it has opportunities to push so that it can ultimately control the spaceship to go through some region. Okay, so I think you see where I'm going with this now. If your robot has enough degrees of freedom to move its foot around roughly arbitrarily, then suddenly the problem gets much simpler again. Your foot, your hand, anything that's allowed to touch the world, is like a little thruster that can only apply force when it happens to be touching something. The force that it can apply is constrained. It's allowed to push. It's not allowed to pull on there unless you have suction, right? And your job is to figure out how to move your center of mass by planning out, I'm going to push on this for a little while, I'm going to push on this for a little while, push for this for a little while. And if I can schedule that series of locations to push, then I can ultimately get through the level and succeed, right? That's a very different view than a compass gate. But actually, once you get enough degrees of freedom, I think that's the most relevant problem. That's the right way to think about how to make a walking robot move around. Okay? So, I mean, to just finish that, right? So if I'm suddenly walking and I've got my robot here with mass, let's say I have a robot that has massless legs, okay? And it's taking a step, then suddenly it's got one thruster here, another thruster here, right? And it's exactly the problems that we just said. And the reason force is allowed to be not just along the axis is because there's friction. But I have some constraints on friction. For instance, I say that Fi of z has got to be greater than or equal to 0. So there's a constraint on this, right? And then Fi of x is going to be less than Fi of z. They're linear constraints on the friction, okay? And they can only be producing force when the foot's not moving. That's the simple case, but until we're doing ice skating or something. Okay, that's basically the problem that we have to deal with in a more complicated robot. Okay, and that's the most relevant problem. So, when does this become meaningful, right? So this is not a good model for the compass gate, even for the need compass gate or whatever. It's going to take more than that. But once you have enough degrees of freedom that you can really move your foot relatively, you can sort of move your foot wherever it needs to go relative to your center of mass, then it becomes a good model. I said, imagine you have massless legs, but actually you don't even need massless legs for this to still be the right way to think about it. I mean, I have made the point that a lot of the successful quadrupeds out there have really light legs, and that is true, but it's not to make this model work. This model actually is still relevant if you have mass in your legs. Because the coordinate that you're trying to control then is now the center of mass. okay, which is XCOM, it is a function of my current joint configurations, a potentially complicated one. But actually, no matter how complicated your robot is, even no matter how it carries its mass, it could have really heavy feet and really light torso. It'd be a sad robot, but I could still say that my goal is just to produce forces at certain points to move the location of my center of mass around. Okay, and then the corresponding, a center of mass is just a position, it's a point. So the corresponding relationship about rotation, the orientation of my humanoid, that's what we worry about, is regulating the total angular momentum around the center of mass. I write COM, center of mass, yeah. Okay. That's the sort of generalization of the point mass, or single rigid body rather, with a mass and inertia. Is just whatever your complicated rigid body is, and think about it regulating its center of mass and total angular momentum. Okay. So there's another thing that we've been thinking a lot about in this picture of hybrid dynamics is the impacts, right? That's complicated a lot of our analysis in general. If you're clever enough in this model, you can even ignore the impacts, okay? So, I'm not necessarily advocating it. I'm just explaining that if you're willing to, for instance, have your center of mass stay at a constant height, okay? So let's say the z position of my center of mass stays at some constant, implying that z dot equals 0, z double dot equals 0, okay, of my center of mass. That seems like sort of a reasonable thing to do, okay? But if you actually accomplish it, if you're able to regulate your center of mass, and similarly, if you are willing to regulate your total angular momentum so that your body angle is effectively 0, so my total change of angular momentum, which I'm capturing with my toy variable here, then if I'm willing to, so that means I'm walking like this, right? It's the thing I hate, okay? But if I'm willing to walk like this and I'm actually regulating my center of mass, which I can do by, center of mass is a simple function of Q, so as my joints are moving around, I can certainly estimate it and try to regulate it. If I manage to keep that completely flat, then I've imparted no energy into the ground when my foot came down. So there was no collision. Right? So if there was a collision, it would change my acceleration of my center of mass. It means to regulate the center of mass perfectly, I actually have to bring my foot down to, if I have a foot with mass. If I have a foot with mass, then that means I actually have to bring it to 0 velocity as I'm touching the ground. Okay, it's kind of a wonky thing to do to really regulate your center of mass. Maybe you can let it go a little bit and you just regulate. But if you keep yourself in this world where you're basically not moving your center of mass, then you get to ignore collisions. Okay? So that's the beginning. You can see how those kind of assumptions are going to make it easier. It still feels like a complicated problem. But it actually turns out that it makes it even easier than what I've shown so far. So getting rid of impact sounds great. Thinking about not worrying about all of the complexity of my joints already sounds great. But it's even better than that. The resulting equations are linear. Up to some, I can basically use convex optimization to move my humanoid around. right? Okay, so let me try to play that out for you. That's worth starting a new board. Any questions so far? I love questions. Okay. So these equations, I showed the picture here and the story here of thinking about thrusters that you can put in certain locations. That works always. It turns out the equations get really simple if you're just walking on flat terrain. So let's think about the special case of flat terrain first. Okay, so if I have a handful of points, I've got a foot over here, let's say, and a foot over here, and I'm trying to control my center of mass and its effective inertia with some forces, some ground reaction forces here. Say those forces are F1, F2, F3, F4, and their locations P1, P2, P3, P4. I used R to be I'll still use this to be R in the relative coordinates, R1, but P is in the world coordinates. Then, what's interesting to understand quickly is that what in this special case where I've got feet on the ground, constraints on the forces like friction or no suction, so a unilateral constraint, they quickly impose limits on what I can actually do moving around my center of mass. The easiest one, of course, is if I say that Fi of z is greater than or equal to 0, always. What does that imply about my ability to move my center of mass?
Up at the acceleration, but not down.
I can't go down faster than gravity, right? I would have to pull on the Earth, and that's just right out of saying that if f of z equals 0, I erased my equations, but it's it's the sum of those z's, sum of those forces that equals minus mg is the z, so that implies that z double dot is going to be greater than or equal to negative g. Similarly, if I say that this thing is limited by friction, at each point I have a Coulomb friction, then that implies something about, just to write these again, that implies something about what I can do to my, in the horizontal plane. Right, so the sum of these things is going to be less than fz. That implies that my x double dot actually can't move faster than, my magnitude of this can't move faster than z double dot plus g. Okay, if I just take this inequality, stick it in here, that just implies something about x double dot too. Okay, which is it's a nice reminder that friction is useful in locomotion, right? If you have no friction, you can neither accelerate nor decelerate. But also, if I was somehow falling at the rate of gravity, even though my feet were on the ground, then I'm applying no force to the ground, and therefore I can't push or pull on the ground, right? This says if I want to move my center of mass this way or this way, I'd better be putting force down and be using friction to do it. That make sense? But what's nice here is that as a planning problem here of trying to figure out how my hovercraft, spacecraft, walking robot is moving through space, that the constraints that we have to write on the force due to friction and contact are actually relatively simple constraints. And they imply something immediately about what my center of mass can do. So if you think about writing a problem of getting this humanoid through an environment, that I'd like to rule out very quickly that I can't do that center of mass trajectory. I can't do that center of mass trajectory because there's just no way I could possibly do that given the force opportunities I have. Okay, so any constraint we can pull over into the center of mass just simplifies my search space a lot. Yeah.
If we were coding this up, the decision variables would, for example, maybe be like fi, comma x, and fi z, right?
So that's exactly. So it depends on how you do it, but the one I'm going to work towards here is that you're going to optimize your center mass trajectory, x double dot, z double dot, at the same time as a surrogate for f and z, which it turns out you can summarize that in a single variable instead of thinking about all of them separately. So you can jointly optimize center mass and forces. Yeah.
And is there ever a problem where, like, you might want to move your force vectors too quickly for your hardware, and if so, how do you optimize around that?
Yep, totally. Thank you for asking questions. Awesome. But I'm going to defer that one because not because I don't want to talk. I actually, but I got a whole page on that coming up. So good. Cool. All right. So force constraints confer constraints on my center of mass. It turns out it's actually even more than that. If I look at my angular momentum sort of constraints, just thinking about the rotation around this as if it was a single rigid body, is the easiest way to derive it. It's Ri Z Fi x minus Ri x Fi Z. Okay. If you break this out, where Ri is pi minus this x z in my notation, right? It's the relative coordinates. If you break this out and do a little algebra, then what you'll see is that this equation implies the following. mz double dot plus mg I forgot to tell you I forgot to define center of pressure for you. So first of all, you know what the center of mass is. That's a familiar concept that we use a lot. If I have a bunch of masses at some location, xi, then the center of mass is a position in R3, right? Or R2 if I'm in the plane, but right, the center of mass is some single point that is sort of the weighted combination of all of the points. So I'm about to use a new term, which I was about to write without defining, but there's some notion of summarizing all of these forces in a single point, which is called the center of pressure, okay? So we're going to do x center of pressure which is defined sort of analogously. It's the average, it's the point, a weighted average of these forces, okay? So it's the sum over just a location on the ground here that I can use to summarize those forces. And it comes up naturally here because when I insert this in here and I take the sum, then I'm going to see this sum of pi x fiz occur a lot. So it's just a way for me to summarize these terms effectively. Okay, so this equation, when simplified in that way, gives me the following relationship. I don't know if that's immediately impressive to you yet, but that's a relationship that I hope you can imagine through a little bit of algebra inserting this in, that this would simplify to that. Okay? And the interesting thing is, if I now take those assumptions that theta double dot equals 0, and z double dot equals 0, z double dot equals 0 also implies that this thing, the location of the center of pressure we know to be on the ground, and that means that the location of the height of the robot stays constant if z double dot, well, I'm going to additionally enforce that this equals 0. Z minus z center of pressure is just some number h. Okay? Height of the robot. So if I'm in this world of walking like this, then my height is just a constant. And this equation simplifies down to x double dot is just negative g over h x COP minus x. Or if I want to flip that around, just to get the sign better, x minus x COP. Okay? Sorry for the algebra, but I wanted you to see where that comes from. And it's actually a big deal. This says so much about that governs sort of the way our robots walk today. Okay? But yes?
Yeah, so even though this would probably be unlikely to be physical, if the ground were exerting just a pure moment on you,
Yeah.
would the center pressure just not be defined? Or is it not useful for that?
So there's a generalization. So center of pressure is sort of particularly useful if you're on the plane and assuming these sort of forces. You can have a center of pressure higher, over a 3D thing. But the generalization of this, which I'm going to define in a minute, is that what you care about are points around which you can summarize all of the forces on my body with a force instead of a force and a moment. So I'm going to write that down in a second, but there's a generalization of center pressure that's going to work better in your crazy cases. Even in the I've got feet at different heights cases, there's a slight generalization of this. But it's simple to think about center of pressure, and it works really well for the flat ground. That's not adding moments to my feet by itself.
I guess I meant if there's just a pure moment, if there's some forces at 0, then the model, I guess,
No, it's a great question. Yeah. So, you can get a pure moment from just having force at your toe and not your heel and stuff like this. But so in those cases, the center pressure does hold. But you will break the center pressure if you push too much. So if you start trying to think about it out of plane and stuff like this, and we're going to generalize it. Okay, read this off to me though, right? So this says the acceleration of my center of mass is completely determined by the location of my center of mass relative to the location of my center of pressure. Okay? So my center of pressure, the forces I'm exerting on the ground, and my center of mass, their dynamics are completely linked. If I know where my center of pressure is and my center of mass is, I know how my center of mass is accelerating. Similarly, I can go the other way, right? If I want to control my center of mass, I can move my center of pressure. If I want to control my center of pressure, I can move my center of mass. They're just linked up like that. They have to be in step. And then the relationship is always is never very complicated, but it's particularly simple, a linear equation, a linear dynamical system. This is a non-minimum phase linear dynamical system, for those of you that think about linear systems a lot. So if you were to leave your center of pressure in a location, then you'd tend to fall down. And similarly, to regulate, you might have to throw your center of pressure away in order to come back. Okay, because the signs there's a little wonky, but the center of mass and center of pressure are completely linked. Okay, so this is actually, this one, I mean, I knew the equation, but it took me a long time to realize how important that was. There was a time, maybe it's still this time, but there was a time where there was this debate between the people who were building position-controlled robots, walking robots, and force-controlled robots. And like Asimo is all got position control throughout. And then like the Leg Lab, for instance, at MIT, they were building series elastic actuators that were able to control torque, but you could still carry them. Force control is going to dominate, There's all these reasons for force control. This equation explains why Asimo can still move around really well, even though it's on position control. You'd like to, the argument originally was if you don't have torque control of your joints, how can you regulate the forces on the ground? You need to, the Neville Hogan, right, the view of the world is that you want to regulate your interaction forces. This equation says to me, you can regulate your interaction forces even with a position-controlled robot. Because if you're moving your center of mass, you're actually controlling your ground reaction forces directly. Asimo's doing a great job of controlling its ground reaction forces. It's not by sensing force and closing some impedance control loop on that. It's by moving its center of mass around, which it can do, assuming that the feet are on the ground, and that's just kinematics. And by regulating the acceleration of the center of mass, it's got to be controlling its center of pressure, at least. Maybe not the details of the force, but the relevant force. Okay? So the center of mass trajectory and the center of pressure trajectory are linked. And in the flat ground case, it's a linear relationship. Okay, so yeah, does that make sense? It took me a really long time to appreciate how important that was. But it changes a lot of things. I think the literature on it is a bit messy. I don't know. A lot of people said roughly that idea with lots of different words, arguing that their words were different than everybody else's words, but it was kind of all the same stuff, and it was a mess. And even today, if you look at it and try to figure out what's going on, it's kind of a mess. So most of the people talk about the zero moment point instead of the center of pressure. Okay. You'll hear that a lot in walking. And you'll see papers where they're like, the whole point of the paper is, everybody's confused about ZMP, let me clarify it. And then you see another paper saying like, that last clarification paper confused everybody about ZMP, so let me write another paper to clarify it. I cited the ones that I think add the most clarity, but there's lots of treatments out there. It's a simple idea, really. Okay, so the zero moment point, what is a zero moment point? So this is almost exactly your question, is that if I have some rigid body and I'm applying a force at some point on that body, right? RF, I've got R cross F. I could always write this as no matter what, or any sum of forces. I've got force 2 over here. I can always summarize the contribution of those forces as, at any point, I can summarize it by a single force plus a torque. right? That's just the total wrench that's being applied on my rigid body by all the forces involved, can be summarized at any point you choose as a force and a torque. That's just rigid, that's just the rigid body dynamics. Okay? There are a few points out there, maybe typically a line of points if you're working in 2D, where the torque that is required to summarize it is 0. Okay? So there might be some special points. For instance, if I only have a single force acting on the body, that's an easy case where that would be my 0 moment point. But even if I have a bunch of forces, there's some summarization point where the way that I describe the influence of those forces on the body, around that point, it's just a force and no torque, right? So, I mean, there's lots of ways to write it, but I think the algebra maybe doesn't matter that much. Yes, it's a 0 moment point is a point in which all of the forces acting on the body can be summarized as just a force and not a torque. The total wrench is just a force. And the key idea is that in the flat ground case, the center of pressure is such a point, is a 0 moment point, okay? The 0 moment point is or the 0 moment points, if it's in 2D, I have a whole line of them potentially, is a meaningful idea even in more complicated configurations, so it sort of does generalize the center of pressure. I just wrote center of mass, I apologize, you should call me on that. Center of pressure is a 0 moment point, okay? So that point of summary on the ground is also special in a mechanics point of view. Not only is it sort of summarizing the forces, it's summarizing that I can think about all of the ground reaction forces as just acting as a single vector of force from that point on the ground. So the center of pressure is special for that extra reason. And that is kind of why some of the equations simplify so quickly. Okay? But it's really no more complicated than that. For flat ground walking, if you just every time someone says 0 moment point, you go, center pressure, then that gets you through a lot of it. And I did that for a little while. But I think, yes?
What happens when you have just a rigid body with two opposing forces in opposite directions? Where is the 0 moment point not just like a one-dimensional?
It's simple enough to derive. Let me see, intuitively. It might be off the body. It doesn't necessarily have to be on the body. So there's some other point off the body that would, be comparable to that. Yeah. Okay. So the magic here now is that we're going to use this linear relationship to find more complicated plans. So when people talk about 0 moment point planning, if we separate out if we separate out and make a first pass, there's a standard sort of walking stack where the first thing you do is you decide where you're going to put your feet, come up with some footstep plan. As a second pass, you're going to then program your center of pressure and center of mass to be consistent with those footstep plans. And then maybe the last pass is you fill in all the details to try to make your legs actually achieve that center of pressure or center of mass. Okay, so now every time you break these down into pieces and assume that they're independent, you get more conservative, but this is pretty common practice. I'll talk about a couple different ways to fill in the details of all your other joints. Okay, so first, since we're thinking about center of mass, center of pressure, let me assume a footstep plan is given and think about how we then define the rest of the solution in our center of mass, center of pressure. So footstep plan, if I'm looking down from above now, I've got some feet that are walking along. This is my left foot, my right foot, okay? At different times, this is like the, follow this way to find the gorillas at the zoo. Footstep down from the top, okay? There's a couple things we know about thinking about by summarizing the ground reaction forces as the center of pressure. So first of all, the center of pressure has to be inside the convex hull of my ground reaction forces. That should maybe be intuitively clear. But if I look at this X center of pressure, since the forces are always, if my forces are always greater than 0, that implies XCOP is inside the convex hull of the positions. How do I see that? Well, if these are always positive, then this is just, if I take this and write this as sum over I, pi, x, fi, z, sum over I, fi, z. This is a number that's between 0 and 1. It's an affine combination of these things. It's going to be inside the convex hull, right? So of course your center of pressure stays inside your convex hull. This convex hull, if you're a walking person, is called the support polygon. If at time 0, I'm standing there with 2 feet like this, I might have a support polygon. If I've only allowed ground reaction forces at my feet, I might have an initial support polygon that looks like the convex hull of my feet. Okay? So a constraint on my initial center of pressure is that it's got to be somewhere inside the convex hull of my support polygon, of my contact points. Okay? And then similarly, as I start walking, if I lift this foot up, the center of pressure is going to have to be inside this foot. If I put this foot down, then I'm going to have a convex hull that looks like this for a moment. If I put this foot down, I'm going to have this convex hull, so I could have a point over here. And the timing, because these are affecting the acceleration of my center of mass, the exact timing of moving this matters, and I'd like to have a continuous center of pressure trajectory. So what people used to do, and for a long time got very far, all the initial Asimo and the like videos, they said once I had a footstep program, which was a trajectory of locations and timings of my footsteps, then I could actually just draw sort of the straight line center of pressure trajectory like this. Just say my center of pressure is going to follow that. And you have to prescribe the timing so that it gets here before you lift off this foot, and you get here before you lift off this foot. Okay? And the like, okay? And then you can just run this equation through to solve for the center of mass trajectory, which ends up doing something like this. It does not have the constraint that it's inside the support polygon, but you can solve for it exactly. Yeah?
If your center of mass is not inside your support polygon, isn't it? Wouldn't your theta dot be theta double dot be something else in there?
So the theta double dot is the rotations around the center of mass, so that's a separate thing. But you can be keeping your center of mass constant and moving this way, right? I could be extending my leg, for instance, in order to.
But like when you lift your left foot,
Yep.
and when your right foot is like to the side, aren't you applying a torque around your center of mass?
You are potentially decelerating your center of mass, for instance. I could still be applying, let's say, resistive torques at my hip in order to have my total angular momentum staying constant, because I'm applying a wrench on the ground, a net wrench on the ground too, right? I understand your question. I know that it's possible to have your center of mass outside without breaking the angular momentum, or maybe it's deviating the angular momentum a little bit. I guess you're right. Let's see. Get this right.
Even for the simple model,
Yeah.
I think if you like leave your left foot from the ground,
Yeah.
your mass needs to be somewhere on your foot to make sure that your tail double dot is not zero.
Yeah, I think you're right that you can, because typically we enforce Z being exactly right, and we regulate angular momentum, the angle. So I think that you're right. It is actually deviating in angular momentum, but you just try to regulate it to be small. You're right about that. Yeah. So. Yeah. So. But the old way to do it here was that you just, so what happens is because of these linear relationships, because of this polygon constraint, it's easy enough to write down some feasible center of pressure trajectory, and that implies a center of mass trajectory. And the interesting thing is, if you were to speed up your plan, if you wanted to walk through the same footstep plan but faster, you run the same equations, and the center of pressure equations could go through this. The center of pressure could go through the same points, but the center of mass actually moves. It changes the center of mass trajectory if I'm going faster. So a slow trajectory will follow the ZMP more closely, but a fast trajectory will actually be right more down the middle. So that was a really interesting experience for us when we were trying to make the real robot walk. And a lot of people have this experience, I think, is that actually walking slowly is harder because you have to get your center mass really over your foot, and you're going back and forth, and you're sort of, once you start walking faster, your center of mass actually doesn't deviate, it doesn't go side to side very much, and it's easier to walk. It demands less of your control system to walk fast, and it's partly because your center mass trajectory is less, and it's implied right from those equations. By the way, I wrote down just the planar version of this, but this works in 3D also. And the nice thing is that the dynamics of the center of mass in the y coordinate are completely independent, given this model of the trajectory in the x coordinate. So these equations are just two of those equations: the x double dot and the y double dot. Yeah.
Quickly overview the how someone would do the footstep plan and when that's not. That is decoupled. So you mentioned that the footstep plan is decoupled from the other footsteps that you get more conservative. Does that mean like there's a geometric sort of heuristic way of doing footstep planning, or is there some sort of algorithmic way of doing it that's still conservative?
So I'll give you the automated one that we've done. In the past, robots walked on flat terrain for a long time, and then they walked on stairs or other things where it was pretty easy or pretty natural to put down footstep plans. When we started the DARPA challenge, we were actually laying down we made a GUI to allow people to put down footsteps sort of automatically, and we increasingly got more sophisticated about doing the footstep planning. I think most people today still plan their footsteps relatively independent of the center of mass, but we have ways to combine a little bit of the dynamics of the center of mass now in the footstep plan, and I'll show you that in a moment. But given this, similarly, given if a footstep plan was planned, it used to be that people would just write the ZMP trajectory or the COP trajectory by hand and prescribe it. Now that we understand that it's a linear set of equations, And the ability for your center of pressure to stay inside a polygon is a linear set of constraints. You can actually use linear optimal control to program, to jointly solve for your center of pressure trajectory and your center of mass trajectory. And I think that is in favor now. Certainly it's in favor in my world. So you can jointly, so if you, for instance, you maybe have a desired center of pressure trajectory that looks like this, and a desired center of mass trajectory that looks like this, but you could say, find the center of mass trajectory that's sort of as with as little effort from my moving around as possible. I could deviate the center of mass as little as possible, subject to some quadratic cost on how close I am to the deviation. Those kind of things now are just a quadratic program. Okay? So that became a linear optimal control problem once the footstep plan is given. Similarly, I mean, it's a particularly easy one. It's just it's an unconstrained one. So you can actually write down the LQR solution to this and stabilize your center of mass given the footstep schedule and the timing. The one that is really, so even when I tell you about footstep planning, the location of the footsteps is actually fairly easy. The timing of the footsteps is gross. I think we still don't have great solutions for when to put your foot in different places. Okay, so let me give you a little bit of window into the way people do footstep planning. The simplest one is, well, there was a time when it was really thought of as an AI problem, where you would just sample a bunch of, using a classical planner, where you'd say, throw down a bunch of possible foot positions, and then try them all and see what works, and do a brute force search on it. I think we can do a little bit better now. But they're based on fairly simple approximations of what the constraints from the humanoid are. So, first thing, actually, I should say is it even depends on what you can get out of your perception system. So at the time, I mean, when we did the DARPA challenge, that was the dark age of perception. That was like 3 years ago or something. And that was before perception really worked. But even then, you could have, from simple point cloud algorithms, you could figure out a lot about the terrain. So we had algorithms that were just doing plane fitting, geometric sort of reasoning about the world, and this is actually the real competition, and it would sort of go through and segment the world into places where you might be able to step or touch, for instance. We didn't do any of the falling and touching the world in the competition, but this is what we wanted to be doing. That was sort of a reasonable thing to expect out of your perception system, even at the time, was that you could sort of, using the depth cameras, you could image the world, look you can compute at every point, so the normals around that point by looking at it, doing sort of a local plane fitting approximation, and then you group points that have similar normals into regions that are sort of flat, regions where you could potentially step. And then the problem becomes an assignment problem of saying, I want this foot to be inside that region, which region do I want each foot to be in at each time? Okay? And that is where, you start writing down more complicated problems. We made a bunch of, and most people make a bunch of sort of simple assumptions, saying if I've got a foot here, then I have to decide what are the reachable regions for my next foot. And maybe kinematically, the robot might have some ability to put its foot down if it was completely stationary, right? And so I could say that maybe there's anything inside this region. This is a top down, the front of the robot. If my left foot's on the ground, there's sort of some set of states where you could potentially put your foot down. As good convex optimization and relaxation people, we would typically approximate this. I made this look like my approximation is going to be really bad, but we would approximate this with a box or an ellipsoidal region here to to make an inner approximation of what the reachable region was. This always felt conservative, not just because there might be some places in the workspace that you can't reach with a convex region, but also because it assumes the robots, for instance, if the robot could jump and get it to a new place, we're never going to find that. This is sort of an inner conservative approximation saying we're going to be in this region. It also means you're not going to be crossing your feet a lot if we're making convex approximations of the reachable set, right? I was joking with somebody after class the other day, but there is something you should always look for in when you're watching humanoid videos, right? There's all these people have videos of push recovery of a robot. You come up and push it, and it takes a step and goes like this. But there is something you can look for that you almost never see in those videos, right? So a lot of times you'll see the robot's walking, and its right foot will be in the air, and someone comes up and pushes it to the right. It's very rare to see someone, when the robot's like this, someone pushes it this way because it has to cross its legs. The quadrupeds are fine. They've got no legs to get in the problem. But the humanoids have a hard time with that because there's all these kinematic constraints and you can't do sort of simple heuristics like this. Okay, something to watch out for. All right, so we started off with sort of a heuristic way to do the footstep planning. We made convex approximations of reachable sets, and then we started doing, for instance, nonlinear trajectory optimization to try to plan down a set of footsteps. Given I have the reachable set of the robot, I have some admissible regions where I can step coming from my perception system. Right, and I have to find an assignment of each of those footsteps that's inside this, in the order that goes through. We did a nonlinear optimization to begin with, and we ended up with a mixed integer optimization where we explicitly had the assignment of foot to region as an integer variable in our optimization, and we used an MI convex solver to plan our footsteps. And that actually works very well up to the conservatism of those approximations, right? So that was this thing I showed you quickly last time. The regions now here you can appreciate they are inside the full step of the full actual region here, because the center of the foot has to be inside this set in order for the entire foot to be on the region. So sort of the configuration space regions that are admissible for that robot to step in that place. And then a mixed integer convex optimization would assign not only the continuous location of the foot, but also the assignment of foot to region. The reason this is in the video is because that was the case. All right, so basically, we had to walk through doors with the robot. It was like the disaster response scenario. We had to open a door, get up and walk through. The stupid robot was too big for the door, right? So it was like Hans and Franz, where you had to sort of walk through like this. They actually changed the robot halfway through. They flipped the elbows over so we could fit through a door, and at the end we walked through like this. That was good. But for a really long time, like the hardest footstep problem we had was doing this Hans and Franz thing. And Robin, who's an amazing student working on this at the time, he was the one who was putting down footsteps by hand. And he's like, screw that, I'm going to write a footstep planner. And that became his research. He's like, I'm never going to put down footsteps by hand again to pilot the robot through the door. It's ridiculous. So motivated good research for ridiculous reasons. Okay, so that's probably enough to say about footstep planning, is that there are heuristic ways. People do, sampling based. You can find all of them in the literature. There's sampling based. There's a lot of people that do nonlinear trajectory optimization based. And then we advocated for mixed integer convex optimization based. But all of them using very simple models, if any models, using simplified kinematics. And almost no dynamics. Now, we got to by the end, though, was if you're willing to keep your center of mass at a constant height, then you could start putting these objectives, this objective of trying to optimize your center of mass and center of pressure location jointly with the foot locations. But it's hard because as soon as you get the extra terms, if you have the location of your foot also as a decision variable, then again that becomes bilinear in the optimization, so it's not mixed integer convex. So we would have to make a lot of approximations to that. And that was the point where we were getting where we'd start trying to put, and I think that's still the state of the field, is that we're trying to put more and more dynamics into these formulations that can sort of jointly solve for the footstep planning and the center of mass, center of pressure trajectory. That's, people are still thinking a lot about that. I could say it sort of here, right? So if you want to plan with a little bit more dynamics, you want to include the dynamics of your center of mass and angular momentum while you're doing your foot positions. The reason that gets hard is because suddenly, if the position of your foot and the forces roughly are decision variables, then you have these bilinear terms. Okay? So even these bilinear terms, there are standard convex relaxations and especially mixed integer convex relaxations where you just try to break that up into simpler and simpler functions in order to make it work, but they're always conservative and expensive potentially. So, but with that recipe, we got to the point where we could do joint footstep planning and center of mass, center of pressure trajectory planning on more complicated robots that even had aerial phases. So it looks like this. This was Little Dog. Yeah, so if we want Little Dog to bound across the terrain, then we would actually have our perception system, or we would come up with some potential contact regions where a foot could be assigned to any one of those regions. Similarly, we have said that a foot could be assigned to the free space region, the region above the ground, and at every instant in time, each foot has to be assigned to one of those regions, either the contact region or the free space region, okay? And each of those individually are convex constraints, but the assignment problem becomes an integer constraint in our optimization. But if you put that in, you can have a mixed integer convex optimization that can plan, more dynamic, more aggressive maneuvers of the locomotion. Still with our, just thinking about the location of the contact, that's why we drew the silly little legs, right? The location of the contact is sort of abstracted away. You think about that first. And then once you have a feasible plan from that, you can give that to a full nonlinear optimization to sort of fill in the details. And it's not guaranteed to succeed. It could be that you found a feasible problem, trajectory in your convex optimization, and then you're unable to find the full nonlinear solution. But in practice, it did succeed most of the time. To the point where, these are things that we would be willing to run on the robot at runtime. This is sort of getting towards more reliable trajectory optimization. Yes, please.
Is this still position control or is this force control?
This is a trajectory that's played back with, it does not need to know the forces at the joints. I think in simulation we often assumed we had torque there, but I believe that as long as you're able to regulate your center of mass trajectory, it could be done with a position-controlled robot. Yeah.
Could you repeat the thing you said before you answered the question? You mentioned that first think about footstep planning and then you go into detail, and sometimes it doesn't work, but most of the time it did. Could you maybe elaborate a bit on what you meant there?
So remember the idea that we had where you could sort of cheat and have force at a distance? That was one way to make the contact planning problem easier. The relaxation, so it's the angular momentum is what kills you here, this R cross F. So what we do is instead of saying R cross, that R and F have to be exactly on the line R cross F, we say it's going to be in some region around R cross F. So that means we're assuming that we could get an angular momentum that may be aphysical. Okay? but we can make that as tight as we want with at more cost for the optimization. So what happens is we sort of, we plan with the, this sort of hand of God that could potentially stabilize the robot. And when we take that away, if our relaxation was too loose, then it could be that there was not actually a feasible trajectory there. So there's a balance between how expensive that optimization is versus how, and how tight those are. And the way that you do that is, so the R cross F is some number curve, right? Is if I were to just say R cross F equals 2 or 1 or something, it looks like this, right? So what we do is we approximate it with a region that looks like this, for instance, is our first thing. And then if that's way too conservative, which it almost always is, then we'll actually split it up into 2 regions like this. And then if that's too conservative, we can sort of carve it up with more and more pieces. But then there's an extra integer variable which says I'm in this piece or I'm in this piece. And so it gets more and more expensive to solve. Sure. And Nick, did I ever get your footstep planning question solved?
I think so.
Yeah, something like that. Okay. So this, I think, is the right way to think about, well, there's many different ways to do planning. But I do think that there's something fundamental that happened in the humanoid, the legged world, which is that you ignore your dynamics, of your detailed dynamics, and you think about your center of mass, you think about your contact locations, and then you fill in your details later. And we were excited enough about this idea and my neighbor was at NYU film school, so we said, okay, this is how you do parkour, right? So when this guy's doing parkour, what he's thinking about is which contact regions he should be putting his hands and feet in, right? And then, he's doing amazing things to get there, I have no doubt, but the right way to plan parkour for a robot maybe is to find that abstraction first, fill in the details on a second pass. And we got, kind of far. My kids were watching Ninja Warrior at the time we were doing this, so, we had Atlas doing salmon ladders and monkey bars and stuff like that, right? So the planners actually could solve for pretty non-trivial things. And if I had time, I would tell you about the stabilization, but it's pretty simple about how you actually stabilize those controllers. That's the most important point. So now, if someone asks you, why does a robot go like this, you guys have to have the answer, right? Now you know why humanoids walk. Constant center of mass, no impact event, linear center of mass dynamics, and contact optimization. That's sort of the big story. Okay, that's why even though planning a compass gate, finding a limit cycle for a compass gate is hard, but we can have Asimo, running through an office environment. That's why, right?
Yeah. So you mentioned the concept of placement for parkour, which is a generalization of a kind of running operation. But you wouldn't be able to make these assumptions at all for it has an aerial phase where you have to have impact, right?
Good.
So
a
similar abstraction technique for that.
These equations are still not very hard when you have impact, and they still justify thinking about center of mass, center of and angular momentum first, and then filling in your leg kinematics later. So that's completely justified, and that's the recommendation here. You can still not have impact if you're running, but it's kind of kooky. But you could be coming down, and if your foot is coming up at the same speed that you have hit with zero velocity, right, and then absorb it all into your leg. Okay, that sounds batty, but actually some of the robots that run are roughly doing that. The ones that ignore the impact dynamics, or you treat that as a disturbance, and you try to minimize it. So people get farther than you might think, possibly with not what you'd consider. I guess maybe, I don't know. I'm a barefoot runner, so you're supposed to be zero impact. I think that's good. Actually, I changed my mind. That's exactly the right thing to do. These equations are right. Okay, what else? Yes.
So in the model, we assume that we're controlling the forces the feet, but the actual robot, you're controlling the torques of the joints, right? So is there like an easy conversion from the forces that you found?
It's a really good question, and it's not actually that we're controlling the forces at the feet. The recipe here is that this prescribes ultimately a center of mass trajectory. So if I have the kinematics of my feet and I've stayed inside the friction cone, which I'm going to stay inside the friction cone if my center of pressure is inside. I certainly won't tip off the this. Then if I just move through the kinematic trajectory to make my center of mass do the right thing, then I am controlling my ground reaction forces. That's the big idea. That's why these highly geared harmonic drive actuated robots are able to do really dynamic things. You control your center of mass, you control your ground reaction forces. Yeah?
Actually, one more question.
Sure.
So, like while Asimo is running, if you were to stop Asimo, like all the joints and stuff at this point, like when one of its leg is up, would it stay stable? Like, is it like always going through like this?
Awesome. No. So that's the question you were asking before. This criteria of keeping your center of pressure inside the support polygon is less conservative than static walking. Center of mass inside the support polygon is static walking, which means that if I were to stop at any time, or quasi-static walking, if I were to stop at any time, I would not fall down. The ZMP, you're actually always falling down, potentially, and it's okay. The ZMP gives you a way to plan that.
This might be beyond the limits of this, but if you're on I guess there's not a lot of robots that walk on moving boats, but you have something where like the ground is moving, you have to interaction with dynamics, you just have to start over, or can you extend this sort of thing to deal with something where you're
And to some extent, this gets into, so we've seen less of this story play out in manipulation. It should. I think the right way to do manipulation is probably something about you simplify the dynamics of the thing you're manipulating. You think about its centroidal, its center of mass, its angular momentum, and worry about the details later. But as the geometry gets more complicated, you spend all your time thinking about the geometry, and the dynamics matter less. So I think if maybe the running on boats is somewhere in between the two, you'd probably want to find the right abstraction. If the world is responding to you more, then it's not as simple probably as just thinking about your center of mass of your robot. But we'd have to write down a particular example to think about it. It's a good question. Okay, cool. Thank you for asking more questions. That was great. No class Tuesday because of the marathon, right? So, well, sort of.
Can we still send you questions about protocols?
Of course, yeah, definitely. A lot of people have, and it's good. I think it's good to get feedback.